Chemistry time.
It's kind of disappointing that you've been doing this for all year. Do not have a theme song.
Kind of. A mole is a unit. I
No,
think it's copyrighted.
that's not your song.
And it's also copyrighted. Okay, we're talking about
time.
states of, write this down please, states of matter.
In our head host.
States of matter. Let's list some of the common states of matter to begin with.
Liquid, solid, gas, plasma. Plasma.
I wish that we had named them in this way though. Solids first.
Solid. To liquid.
Gases, I guess we could say, and plasmas. Which of these is the most common in the universe?
Gas. I would say plasma.
It's plasma. Most of the mass in the universe is concentrated in stars, which are plasma.
And lightning.
And lightning, but that's not obvious. That's not most of the matter. Most of the matter on Earth is the other three. And plasma is really quite rare, only in like fluorescent lights and lightning.
There's plasma in your blood?
Yeah,
No, what's a different word? It has the same root word, but the plasma in your blood is a totally different thing from the state of matter plasma. And it is not the state of matter plasma.
Okay.
I forget what the root word is, but I think it's the same root word as plastic. Just means kind of like gooey stuff. So the plasma in your blood is named after that, and the plasma in state of matter is kind of named after that because it kind of flows like a gas, but it has different properties, probably because it's magnetic. I don't know if any of that's true, but the plasma as a state of matter, or the plasma in your blood? Yes, you can, not to me.
I thought so.
Anyway.
Well, I was thinking off.
When a solid becomes a liquid, it's called?
Solidification?
No. When a solid becomes a liquid, it's called melting. When a liquid becomes a solid, it's called?
Freezing. Oh, you're freezing. Weird.
Freezing. When a liquid becomes a gas, it's called?
Evaporation?
Sometimes, but we really correctly call it vaporization, which also includes boiling. Vaporization. When a gas becomes a liquid?
Condensation.
Mm-hmm. When a gas becomes a plasma?
Plasmization.
Ionization. This word is very closely related to the word ion. What's an ion in chemistry? Ooh, that's a rough question to ask some chemistry kids who might not remember and make fools of themselves. What's an ion?
It's an electron that has unstable.
It's a charged atom. It's not an atom has to be neutral, but we can think of it as the charged version of an atom. So what happens is when a gas, which is made of atoms, gets enough energy, the electrons are removed from that, and that becomes a plasma. And because the electrons are no longer with it, it has a charge, and then the electrons have a charge too, which is why we call this ionization. And then when a plasma becomes a gas, I've heard it called deionization. That means another thing in chemistry too, though, but that's fine for now. So we know what all the states of matter, the common states of matter. There are more. There are something like a dozen more states of matter that are fairly rare. Things like Bose-Einstein condensate. What are some other ones? Superfluid. There are some other states of matter, but these are the four most common, or the ones that we talk about the most, and these are the verbs we use when one changes to another. The next thing we're going to talk about, all this is going to be in the first one specifically about gases. So one thing we talk about with gases is this idea of the kinetic theory of matter. The kinetic theory of matter. Kinetic is a word meaning what? Yeah, movement. Like kinetic energy is the energy something has because of its movement. It's the same word as the word cinema. Is the movie. In Greek they would pronounce that kinema. So the kinetic theory of matter is talking about how what that makes up gas, or of everything. The particles that make up all matter are in motion. In a gas, in gases, those particles, what are they doing in a gas? What verb could we use to describe the motion of the particles in a gas?
I'm sorry, can you show me?
They're jumping. I usually say bouncing, but jumping is fine. In gases, those particles... The least restricted. Those particles are
in gases.
bouncing.
Okay. In gases.
in gases, those particles are bouncing. They're bouncing off of each other, they're bouncing off the walls of their container.
Would you say like it's like out of all like the three main ones, it's like the less restricted? Because you know, like solids don't, they're like compacted in.
Yeah. In fact, for a given substance, the one with the most, the state of matter with the most energy, as we add energy into a substance, the plasma has the most energy. So if I do this, most energy for a given substance, obviously something like, for instance, I could have a cool gas. The air in this room is something like 70 degrees Fahrenheit. My tea could be a warm liquid and have more energy than the air in the room. But for a given substance, because we're comparing two different things, right? The tea, which is mostly water, and air, which so those are different substances. But for one given substance, it has more energy as it goes through the states of the matter in this direction, least energy. So for a given thing, a solid would have the least molecular motion, and its plasma would have the most molecular motion. Think about water. Ice cube of a certain mass has less energy than that same mass of liquid water, just because the particles are moving slower. Same thing, that same mass of water vapor has faster moving particles, and a plasma of that water would have the fastest moving particles. They have the most energy. Even for anything, not just gases, but for everything, as particle motion increases, what increases about it?
As particle motion increases.
As particle motion increases, the
energy.
what? Yeah, the energy. The energy, specifically what kind of energy?
Kinetic.
Increases, yep. Kinetic energy increases, and we can measure this when the kinetic energy of particles increase. On a macro scale, we can measure those particles' increased energy as a change in what?
Motion?
No, because we can't see it.
Say it again?
Yeah, temperature. And temperature. All temperature is a way of measuring the average energy of the particles, mostly their kinetic energy, and temperature increases.
So like, I don't really remember what I was saying, but like, if it's in something about like if it's in a more confined space, and it gets hotter in that space because the particles are moving.
Yep, that relates to the gas laws, and we're going to talk about the gas laws.
Okay.
They have their own chapter, which is chapter 13. For now, we're just getting like a basis of the concepts behind gases. Two equations that you need to write down. Three equations that you need to write down. Graham's law of effusion.
Are you gonna write them?
Yeah.
Graham's law of what?
Graham's law of effusion. These are both still about gases. Graham's law of effusion is actually pronounced effusion, but I'm emphasizing the E to differentiate it with the next one, which is diffusion.
Is it still Graham?
Yeah, they're both Graham's law of effusion and diffusion. Effusion is the rate of effusion.
Diffusion.
We don't do very much math with this because this means proportional to. There is a constant that helps us to actually solve this, but you should understand that this should let me scroll? Yep. Basically, very simply, the lower the molar mass of a gas. Can you find molar mass? You guys know how to find molar mass, right?
Molar mass.
Yeah. You know.
I these have an eraser, Mr. Connor. I'm sorry.
You guys know how to find molar mass, right?
Yeah.
The lower the molar mass, the faster it will effuse. And that's one of your vocab words. What's it mean to effuse?
Well, diffuse is like a diffuser.
Yes, diffuse means for the gas to kind of spread out to fill its container.
So would that...
Effuse means for the gas to escape through a little hole.
Okay.
So the lighter it is, the faster it will escape effectively. And then the law of diffusion is the rate of A. The reason we have two of them for this is that
rate of A over...
because diffusion is talking about the movement of two different...
B? Is that rate of B?
Yep. when gases are effusing, they're escaping. The little balloon with a hole in it would be effusion. It's just one gas is all we're talking about. But when it's diffusing, this should be diffusion, not diffusion. That's not a real thing. Diffusion. Anyway, when it's diffusing, it's one gas spreading out through another. So for instance, the classic example of this is that if, what's a gas you can smell?
Lavender. Like infused, like, you know, if you have a diffuser.
Let's pretend that lavender is a gas.
Well, like,
I know what you mean. The volatile chemical compounds, what we call VOCs, the volatile organic compounds that make lavender smell like lavender are gases. That's what makes them volatile. Anyway, if we have lavender, a little pot of lavender oil, which is volatile and therefore releasing volatile organic compounds, which are gases, into the air, if I have that pot over here, eventually Hayes will be able to smell it because of diffusion. It's spreading. Unlike effusion, it's not just spreading out of a hole all by itself, it's spreading through the air. And so in this case, we would use the molar mass of the air divided by the molar mass of the lavender, square root of all that. Because it depends on the densities of two gases.
So if you have a diffuser in a room, isn't it effusing out of your diffuser?
Well, like, there's air
because
in
there's
there
like
too.
a hole.
But there's air in there too.
Oh, so it cannot have
Yeah, it's a mixture. They're both a mixture.
Isn't air a gas though?
The book talks a little bit about pressure too and the pressure units. You need to know those for this test, but they're all vocab, and we will talk more about them in depth in chapter 13, so we're going to move on past that. The last kind of math that you need for this is...
Wait, if we're going to need them on a test, can you review them real quick?
The vocab words, you can read your own vocab words. Dalton's law, the next thing we're going to do is Dalton's law of partial. They're also things, Tyler, that we had done in physical science, so you should probably remember them. But right now we're going to keep taking notes and you can review them later. Dalton's law of partial pressures. This is really pretty easy, I think. All it is that the sum of the pressures, this little capital sigma means sum of, you've seen that before. Sum of the pressures equals P1 plus P2 plus P3, etc. forever.
What's that P word?
Partial pressure.
Partial
Pressure. What this allows us to do is that basically if we know the pressure of a mixture of gases, sum of P, and we know that it's made of three different gases and we know the pressure of two of them, we can find the pressure of the third. Or, similarly, if we know the pressure of three different gases, it doesn't have to be three, it could be any number. If we know the pressure of two different gases, we can just add them together to find the sum of the pressures. That's it, that's all it is. It's just adding. So if you know the pressure, the book says, a mixture of oxygen, carbon dioxide, and nitrogen has a total pressure of 0.97 atmosphere. What is the partial pressure of oxygen if the partial pressure of carbon dioxide is 0.7 atmosphere and the partial pressure of nitrogen is 0.12 atmosphere? All you have to do is add them together. It's just addition. It's just addition. Just adding together your givens, finding the find. Do you have questions about any of these three? They're more like conceptual equations where they're going to help us think about things, but I don't think that there's going to be any actual numerical math on your test about them. But do you see how these can kind of help us understand effusion, diffusion, and partial pressures? No. Okay, how can I help you, Natalie?
No, I have no questions.
Oh, you have no questions. That's better. Okay, let's move on to, we're going to talk now about, really to follow the thing I already have set up, I probably should do liquids next, but, well, that's fine. We'll do liquids next. Boy, this erases so much better horizontally. Liquids.
No, erase horizontally because you look at much of it, the kids will laugh at you.
Not laugh at you, they'll fall in love.
And the guy saw you doing that and the guy looked over at this class and he goes,
Some things that we need to think about when we think about liquids are, and one of these is a vocab word, but we're going to talk about just a little bit anyway. Fluidity, which is not a vocab word, and that just means the ability of it to flow. It's almost like you can think about it as the inverse of viscosity. Fluidity is ability to flow and mix. Kind of like diffusion was in gases. Gases have fluidity too. They flow. Gases are fluids. Plasma is fluid. Liquids are fluid. Some solids can behave as fluids. For instance, if we have like a sack of rice, you can pour it like a liquid, but even though it is a solid. A fluid is just any substance that can flow. And the other one is viscosity, which we can think of as the resistance of a fluid to flow. We just talked before I started the video about the difference between high and low viscosity. Remember, remind yourself, keep these things straight. That to have it more viscous is to mean it flows more slowly, or it's more difficult for it to flow. Blood is more viscous than water. The phrase, blood is thicker than water, you know that? Blood is more viscous than water. It takes more to make it flow. Gasoline is less viscous than water. Another thing this will change is the angle at which it'll pile up. If you have a little pile of honey, like if you pour some honey on a table, it'll probably have a fairly thick little lip, right? Some water will have a thinner little lip. And then a puddle of gasoline or isopropyl alcohol will probably have none at all. It'll just be completely flat. The lowest viscosity liquids can have a layer, can pool up one molecule or atom or formula unit or whatever thick. The amount of beating up that it does depends on the viscosity. Okay? There are other things that determine that. That's a whole field of science called wetting. Not wedding, but wetting. And different things determine that as well. But the reason that all of these things happen, fluidity, viscosity, what we call surface tension, which is another of your vocab words, surface tension, cohesion. You remember cohesion and adhesion with Mr. O? I know he talks about this to you when you're in, I can't remember if it's seventh grade or biology, but
Cohesion.
all of these things are due to what we call intermolecular forces. Intermolecular forces. Okay, come back. To rewind a little bit, what would be an intramolecular force? What's intra mean?
In?
Yeah, inside of. Whereas inter means,
Outside.
well, between two things. You might remember this from biology as
Like
some fluid being intracellular as opposed to intercellular.
Gravity would be the outside one, because gravity
Yeah,
is
for-
between
for-
you and the Earth.
Yes, that would be but you're not a molecule. But yeah, that would be kind of like a metaphor of it. But the intermolecular forces, so intramolecular forces are bonds. Let's just write that above it. Intramolecular forces are the three classic bonds that we're used to talking about. Covalent, ionic, and metallic bonds. The intermolecular forces hold things that are bonded together. One of them is called, and this is a vocab word we're going to talk about a little bit more in depth, dispersion forces. And what happens in this is that when you have even a neutrally like a well-distributed molecule or atom that has all the electrons in it all the way around it, so that they're all hanging out equally. Remember we talked about polar and non-polar covalent bonds? Even if you have one that's non-polar, just because of random fluctuations in the electrons, sometimes it'll so happen that there are slightly more on one end than the other. So it ends up having a partially negative and a partially positive end. And because of this over time, as they all kind of, they all have random movements, there will be some slight attraction between one atom and the next, or one atom and its other neighbor, or one atom and its third neighbor, and which one it's attracted to will change, but the attraction still exists. They'll kind of spend part of the time attracted to other ones just like them. And these are very weak. The dispersion forces are very weak. The book says, the force of attraction between oxygen molecules is called a dispersion force. Dispersion forces are weak forces that result from temporary shifts in the density of electrons in electron clouds. So just because the electrons are randomly moving, they get temporarily a partial positive and a partial negative in, even if they are non-polar molecules. These are very weak, but these give it some surface tension, cohesion, viscosity, and fluidity. The next strongest ones are called dipole forces.
That is Dipole.
It's not dipole, it's dipole. And these ones exist when there's a permanent dipole, what we use this little partial negative and partial positive for. So things like the oxygens and hydrogen in a water molecule. I've drawn these as water molecules. Other things have these. But when there are polar covalent bonds, then it can have dipole forces. Because the negative end of this one is attracted to the positive end of the next one. The negative end of that one is attracted to the positive end of the next one, etc., etc. These are stronger, and therefore all of these things are higher. In a polar substance, all of these will be higher than in a non-polar substance. That's not always true. For instance, oil is non-polar, and it has a higher viscosity than water. But usually, the stronger the intermolecular forces, the higher these things will be. The more surface tension, the more cohesion, etc. And the strongest of all are hydrogen bonds. And this happens in water as well.
What is that one saying? Say stronger.
Stronger. And these are, of the intermolecular forces, these are the strongest.
So it's the stronger the intermolecular forces equals what with more?
Higher viscosity, higher surface tension, higher cohesion, higher adhesion, etc., etc. And the hydrogen bonds, really this picture applies to both. This actually is a hydrogen bond, which is a type of dipole-dipole bond. And that just happens when one of the dipoles is made of hydrogen. They kind of arrange themselves differently, so they have a lattice work. The picture of this you can find it online too if you're watching this later on. But if you look at just type in hydrogen bonds if you're looking at it online in your future life. But on page 413 there's a picture of a hydrogen bond. One special type of dipole-dipole attraction is called a hydrogen bond. A hydrogen bond is a dipole-dipole attraction that occurs between molecules containing a hydrogen atom bonded to a small, highly electronegative atom with at least one lone electron pair. Hydrogen bonds typically dominate both dispersion forces and dipole-dipole forces. So it has to be bonded to something very electronegative, like fluorine or chlorine or oxygen or maybe sulfur or nitrogen. But if that's true, the electrons are much more attracted to the other guy, nitrogen or oxygen or whatever, and they're the hydrogen. And so the dipole, basically what it does is make the dipole-dipole forces even stronger because the dipole is so differentiated. I think, other than, one last thing. We're going to talk real quick about, of course, we need to talk about solids. Do you have questions about the intermolecular forces? Remember, in your mind, they're kind of similar words, but intramolecular mean the forces that hold atoms together to make a compound. Intermolecular means the forces between those compounds. And then write down solids. So solids is the next one. Your book talks about unit cells, which is not really something we want to talk about here. We talked about crystal structure a little bit in earth science, and so if you're interested in it, you can watch the video from like October about crystal structure that we did in earth science. But for now, we're not going to talk about unit cells in here. Solids. So solids would have the lowest energy of all of the states of matter for a given substance. And the main thing I want to talk about is this. So they can be either crystalline or amorphous. And this all has to do with the structure of the atoms in the solid. If the atoms in the solid form a repeating pattern, it's called crystalline. Wait a second, Mr. Keim. If the particles are always moving, how can they ever form a repeating pattern? Answer me.
And solids are more compact, so they really don't move around.
They do still move, but
like
how are
they
they?
shake.
They're moving in place. In the same way that I'm standing up here at the board and just kind of moving about, I'm not moving from place to place. I'm moving in place.
Shake.
That's what they do. Yeah, they just
like vibrate.
Yeah, they're still in motion. They're just in motion in place. This would be a pretty easy thing to just draw. So how can we draw a crystalline solid?
Just a repeating pattern.
Repeating pattern. And how can I draw an amorphous solid?
Wherever you want.
Yeah, no repeating pattern. Not whatever I want, but specifically no repeating. Specifically no repeating pattern. The crystal structure is evidenced in how it looks in the big time, in macro scale. The crystal structure of salt is cubic, and therefore the crystal of salt, even on a large scale, looks cubic. Tell me, Tylee, or Natalie, or Ty, you did this last year, what determines the size of a crystal?
How long it cooled.
Yeah, how long it took to grow. Not necessarily cool, but
like
how long it cooled or how long it
evaporated. Hot longer, the crystals are bigger.
Yep.
But where it's like, if it's like in the sun, it cools faster, so the crystals will have as long.
Exactly. The longer it takes to cool or form, the higher the crystal, or the larger the crystal will get. I think that's probably all I need to show you for solid. So let's move on to this thing called a phase diagram. I'm just going to kind of briefly show you how to read one of these. On a phase diagram we have pressure on the y-axis, almost always. I'm sure you could do this the other way around. We have just pressure compared to temperature. They'll all have different scales. They'll have some numbers on both. But they'll show you they'll have some kind of cockamamie looking structure like this. And they'll say at low temperatures, this will be what? What state of matter would we normally find at low temperatures and low pressures?
I would say salt.
Well,
Because like
maybe
vapors-
at high pressures and low temperatures we find a solid. At high temperatures, high pressure but low temperature, right? Because we can also think of like if we had gas and we put a lot of pressure on it, it would condense also to a liquid. So when we find a liquid here with higher temperature and maybe higher or maybe lower pressure, and then here we might find a gas. And this is just an example. Not always is this the way it is. It could definitely be gas here and solid here. Those would be pretty rare. But a phase diagram just shows us at what...
shows like medium pressure.
Yeah.
High
So for instance, if we were looking at, we could say room temperature was right here. Medium pressure, fairly low temperature, we could call that, we'd say it's a solid. But then we might be able to, using a temperature diagram, that'll tell us at this pressure, we'll call it pressure X, what temperature will it become a gas, and that's temperature Y. This reminds me of another thing I forgot to tell you. There's a word for when it turns right from a solid to a gas without going through a liquid first, like you can see on this diagram, it would do that, right? With a given pressure, this thing would never become a liquid, kind of like what dry ice does. And that's called, if it goes right from solid to gas, I'm going to do this in a different color so I can read it better. Straight from solid to gas, skipping over liquid, is called sublimation. And then the opposite of that, from gas to solid, is called deposition.
It's sublimation.
Yep.
May you please say that all just one more time?
Yep. If it goes right from a solid to gas without becoming liquid, it's called sublimation.
Sublimation. And what if it's a...
Gas to a solid is called deposition. Water can undergo deposition really high in the atmosphere. There can just be some water vapor, and it can solidify without ever becoming a liquid first, without going through condensation. And that can be how some like the cirrus clouds we see in the sky. We were talking about this in earth science. The really wispy, really high clouds. Those are just straight from water vapor to solid water, ice.
That's why they have ice cream.
And the opposite can happen. An example of this would be like, I thought about this when I got into my car one day back in like November, December, and there was just snow all over. Like I opened my car door, there was like instantly a foot of snow in my car. And then several days later, maybe a week later when I came back to my car, it was all gone. It wasn't wet. It had never gotten warm enough to melt. And it had just slowly sublimed. You can even you can put laundry out to dry in the wintertime, and it'll freeze, obviously, right? Your wet laundry, it'll freeze, it'll just be solid ice, and then you can come back 2 or 3 days later and it'll be dry, even though it never melted again, because of sublimation. So water will evaporate from the solid phase even. This is how freezer burn forms in your fridge, or one way that freezer burn can form. You can just have a little ice cube tray and it'll just evaporate. If you leave an ice cube tray full of ice cubes in there, it'll go away if you leave it open. It'll sublime. And then the last thing is that there's this idea of a triple point. This is a vocab word, but the triple point is just where the given pressure and temperature conditions where all three phases of normal matter can exist at once. Solid, liquid, and gas can all exist at once. Each substance has its own phase diagram. This would look completely different for carbon dioxide as it would to water. Look at the one real quick on page 430. This is the phase diagram for carbon. Look, on page 430, instead of the phase diagram for carbon containing the word solid, what does it say instead? It doesn't say solid carbon anywhere. It says diamond and graphite, because there are two different allotropes. You remember the professor from Nottingham talking about that. There are two different allotropes of carbon, two different ways the solid can exist. And so instead of writing solid on the phase diagram, we have carbon and diamond, both of which are solids, but they're different. They're allotropes. Questions about any of this? Questions about gases? Questions about liquids? Questions about solids? How are you doing today?
Tired.
Tired. Bye.